Hello, everyone. Good morning and even good afternoon, everybody. Today, we are really happy to have our guest, Yihan Du from Tsinghua University. Yihan is right now 5th year PhD student at the Institute for Interdisciplinary Information Science, headed by Andrew Yao in Tsinghua University. Advised by Longbo Huang, and she was research intern at Microsoft Research Asia, supervised by Dr. Wei Chen, HBE Fellow and Director, and also a visiting PhD student at Cornell University, supervised by Professor Sun Wen. She is broadly interested in the area of machine learning, with emphasis on online learning, reinforcement learning, and representational learning. Let's welcome again Yihan to give us her research, risk-aware online decision making. Hi, Yihan, please get started.
Hi, thank you. Thanks, Jinfeng, for the nice introduction. It's my great honor to give a talk in this nice seminar. And good afternoon and good morning, everyone. I'm Yihan Du. Today, I'm going to talk about risk-aware online decision making. Online decision making is a very important problem which can be found in many real-world scenarios, including clinical trials, recommendation systems, and online advertising. There are two fundamental mathematical models used to formulate online decision-making, that is multi-embedded and reinforcement learning. And first, I would like to briefly introduce the background of multi-embedded. Multi-embedded is a classic online learning model. In this model, an agent is given K options. Here, an option is often called an arm. Each arm I has an unknown reward distribution, and we use mu I to denote the expected reward of arm I. We define the optimal arm as the arm which has the maximum expected reward. At each time step t, we first choose an arm AT to sample, and then we observe a random reward drawn from the reward distribution of the chosen arm. And we define the regret as the cumulative gap of the expected rewards between the optimal arm and the arms we actually choose. So in this model, the goal of the agent is to maximize the expected cumulative reward, which is equivalent to minimizing the regret. This model characterizes the trade-off between the exploration and the exploitation in many online decision-making scenarios, and finds many applications such as clinical trials, robotics, and online advertising. Traditional online learning algorithms mainly focus on how to maximize the expected reward. However, in many real-world risk-sensitive and safety-critical applications, such as clinical trials and finance, maximizing the expected reward is not enough. We not only want to maximize the expected reward, we also want to control the risk during decision-making. While there have been several existing risk-aware models, such as mean variance bandit, these models only consider the risk measures of individual arms, like variance. And these models only consider selecting a single arm at each time, which means that in their model, the decision space they consider is discrete. However, in many risk-sensitive applications, we often need to select a weight vector or multiple options, which means that the decision space we face is often continuous, and the correlation among different options is often critical to our decision making. For example, in clinical trials, we often need to select a treatment constituted by different correlated drugs, and the correlation among different drugs is often important to our decision making. As another example, in finance, we often need to construct a portfolio constituted or construct a portfolio of multiple correlated assets, and the correlation among different assets is also very important to our investment decisions. Motivated by this fact, we propose a novel risk-aware online learning model called mean covariance bandit. This model is the first to consider the covariance among options into risk measures. And in this work, we theoretically quantify how option correlations will influence online decision making. Next, I will introduce the problem formulation of our mean covariance bandit model. In our model, an agent is given D options, and these D options are associated with an unknown joint reward distribution with mean theta star and the covariance matrix sigma star. Our decision is to select a weight vector W on these D options, which means that our decision space is a probability simplex in RD. And we define the mean covariance utility function as a linear combination between the expected reward and the covariance-based risk term. Here, rho is a risk-sensitive parameter. The larger rho is, the more risk-sensitive the agent is. We define the optimal action as the action which has the maximum mean covariance utility. At each time step t, the environment first generates an underlying random reward vector, theta t. And then the agent selects an action, wt, and observes full or partial theta t according to different feedback settings. In this work, we consider 3 kinds of different feedback settings, such as full information feedback, semi-banded feedback, and full banded feedback. In the full information feedback setting, we can observe all dimensions of theta t. And in semi-banded feedback setting, we only observe the dimensions that we place positive weights on, which means that we only observe the feedback from the dimensions that we choose. In the full banded feedback setting, this is a very limited and challenging feedback setting. We can only observe the inner product of Wt and theta t. So we only observe an aggregated feedback. I will introduce the setting later in detail. And we define the regret as the cumulative gap of the mean covariance utilities between the optimal action and the action we actually choose. In this model, the goal of the agent is to maximize the cumulative mean covariance utility, which is equivalent to minimizing the regret. Next, I will introduce the first feedback setting, for information feedback. In this setting, we select a weight vector at each time step t, and we observe all dimensions of theta t. This feedback setting is motivated from stock investments. In stock markets, no matter what decision we made, we can always observe the prices of all stocks. For this setting, we design a simple and efficient algorithm, MC empirical. In this algorithm, we use the empirical mean and empirical covariance to establish an empirical mean covariance function. And we always choose the action which has the maximum empirical mean covariance utility. While this algorithm looks very intuitive, our main challenge here is how to incorporate the covariance information in our regret bound and to show the influences of covariance on our learning performance. For this algorithm, we provide a rigorous regret guarantee. From Theorem 1, we can see that the regret of our algorithm, MC empirical, is upper bounded by square root of t. Here, t is the number of time steps we play. This result is the first to quantify the influence of arbitrary correlation structures on online decision-making. Specifically, the covariance matrix-based term will shrink from positive correlation to negative correlation, which means that if the covariance matrix sigma star is positively correlate, we will obtain a higher regret. If sigma star is negatively correlate, we will obtain a lower regret. The intuition behind is that positive correlation will enlarge the confidence region of our estimation. In contrast, negative correlation will narrow the confidence region of our estimation. In order to validate the optimality of our algorithm, we also provide a lower bound of square root t to demonstrate that our algorithm is near optimal with respect to t. Next, I will introduce the second feedback setting, semi-banding feedback. In this setting, we consider our decision space as a restricted probability simplex. Because in this setting, we only observe the feedback from the dimensions that we put positive weights on. Imagine that if we assign a sufficiently small weight on each dimension, then this setting will reduce to the first setting. In order to exclude this trivial case, we consider a limited and constrained probability simplex in RD. Specifically, we will constrain our weights put on each dimension to be no smaller than a given constant C. For this feedback setting is motivated from business investment. In business investment, we can only observe feedback only if we investment a program. For this feedback setting, we design an optimism-based algorithm, MCUCB. In this algorithm, we use the optimistic covariance information to construct a confidence region for the expected reward. And we establish an optimistic covariance function. We select the action with the maximum optimistic covariance information with the maximum optimistic covariance utility. So this algorithm is uses a classic UCB framework, and but we use the optimistic covariance information to establish a confidence region. And then we can incorporate the covariance information in our regret results. For this algorithm, we also established a rigorous regret guarantee. From Theorem 2, we can see that the regret of our MCUCB algorithm is bounded by square root of t. Here, the square root of t regret is near optimal with respect to t, and this result also captures the effects of option covariance. Specifically, the positive correlation will lead to a larger covariance matrix factor, sigma star norm, than the negative correlation or the independent case. The intuition behind it is that option covariance will influence the concentration rate of the estimation of the expected reward. The final feedback setting is full-banded feedback. This is a very challenging and limited feedback setting. In this setting, our decision is to select a weight vector on a d-dimensional simplex, probability simplex, and we only observe the inner product of WT and theta t. This feedback setting is motivated from clinical trials. In clinical trials, once we select a treatment constituted by multiple different drugs, we can only observe the aggregated feedback. For this feedback setting, we design explore it style algorithm, MCETE. In this algorithm, we first design an action set, pi, with feature matrices, B pi and C pi. B pi and C pi stores the mean information and the covariance information of the action set pi. And during the exploration, we first put the actions in pi, and we estimate the mean and the covariance using the feature matrices B pi and C pi. And then in the exploitation phase, we just select the empirical best action based on our estimation in the exploration phase. For this algorithm, we provide a regret bound in T up to 2/3. From theorem 3, we can see that the regret order of MCETE is higher than our algorithms in the first two feedback settings. This is because full-banded feedback is a more challenging feedback setting than the first two feedback settings. In this setting, we can only fix the action set to estimate the covariance matrix. So it's still an open problem how to adaptively sample and estimate covariance matrix under such a limited feedback setting. In our regret bound for full-banded feedback setting, the choice of the design action set pi will affect the factor sigma star pi in our regret bound. And here, sigma star pi can be regarded as a uniform representation of the covariance matrix. This result also reflects the influence of option covariance. Positive correlation will give a larger factor, sigma star pi, and lead to a higher regret. By contrast, negative correlation will give a smaller factor, sigma pi star, and will lead to a lower regret. In order to validate the effectiveness of our algorithm and validate our theoretical analysis, we also conduct experiments on both synthetic data sets and the real-world finance data sets. From our experimental results, we can see that our algorithm, the radar curve, achieves a significantly lower regret bound than the baselines, like the 09 gradient descent baseline and the linear objective-based baseline. Furthermore, we also study risk-aware online decision-making under the RL framework. RL is a more general online decision-making model than multi-unbounded. Compared to bandit, RL further characterizes the change of states through time. RL is successfully used in many fields like game playing, autonomous driving, and robotics. Traditional RL algorithms mainly focus on how to maximize the expected reward and cannot control the risk of getting into catastrophic states. However, in many real-world risk-sensitive and safety-critical applications, such as treatment planning and autonomous driving, we not only want to maximize the expected reward, we also want to avoid disastrous situations, such as serious treatment failures and traffic accidents, which means that we want to guarantee the safety while pursuing high rewards. Witnessing this fact, we propose a novel risk-sensitive RL model called iterative civil RL. In this model, our goal is to maximize the worst alpha tail of the reward to go at each step. In other words, we want to ensure a good performance even under bad situations. This model is more suitable for real-world risk-sensitive and safety-critical applications. For example, imagine that we want to fly an unmanned helicopter to complete a task. At each time during execution, there is a small probability that the helicopter will encounter a sensing or control value and does not take the described action. In this case, to guarantee the safety of the helicopter and the surrounding environments and the surrounding workers, we need to guarantee that even if the failures occur, our policy should ensure that the helicopter will not crash and cause fatal damage. As another example, in treatment planning, at each therapy phase, there is a small probability that the treatment will fail. In this case, to guarantee the safety of the patient, we should make sure that our policy can guarantee the safety of the patient even if the treatment fails. Next, I will introduce the problem formulation of our iterative civil RL model. And before this, I would like to first briefly review the formulation of classic MDP and RL. In episodic Markov decision process, there are a space of steps S and a space of actions A. We use H to denote the number of steps in each episode. There is an unknown transition distribution P. Ps prime SA gives the probability of transitioning to state S prime if action A is taken in state S. There is a deterministic reward function R. RSA gives the reward of taking action A in state S. We define a policy pi as a collection of H mappings from S to A. Pi HS gives what action to take in state S at step H. The episodic RL game proceeds by episodes, and each episode has H steps. In each episode K, the agent first chooses a policy pi K. Then the agent starts from an initial state S1. At each step H, the agent first observes the current state SH and takes an action AH according to her policy pi K. Then the agent receives a reward R and transitions to a next state SH plus 1 according to the underlying transition distribution of the environment. After an episode, the agent updates her estimation and updates her policy, and then she will enter the next episode. In order to quantify our performance in RL, we define the stat value function V and the stat action value function Q. V and Q give the expected cumulative reward starting from S and SA at step H and the policy pi, respectively. According to the classic results in RL, there exists an optimal policy, pi star, which always gives the maximum value for all stats and all steps. We use V star and Q star to denote the value functions of the optimal policy, pi star. There is a well-known dynamic programming procedure called Bellman equations used to compute the value functions. Any policy pi satisfies this Bellman equation, and the optimal policy pi star satisfies this Bellman optimality equation. In classic RL, we define the regret as the cumulative gap of values between the optimal policy and the policy we actually choose. So in classic RL, the goal of the agent is to maximize the expected cumulative reward, which is equivalent to minimizing the regret. In our risk-sensitive RL model, iterative CIVA RL, we do not consider the classic expectation of maximization. Instead, we consider a popular risk measure called conditional value at risk, CVAR. Consider a random variable x. Given a risk level parameter alpha, the value at risk var x denotes the alpha quantile of x, and the conditional value at risk CVAR x measures the expected value of the alpha portion tail of x. CVAR is a very popular risk measure and widely used in many fields like finance and engineering. In our iterative CIVA RL model, we change the classic expectation operator to the CIVA operator in order to place more focus on the worst alpha portion successor stats. In order to better understand the worst alpha portion successor stats, we give a simple example here. In this example, starting from SA, there is a half probability to transition to S1, and there is another half probability to transition to S2. In this example, S1 has a lower value than S2. So in this example, S1 is a bad successor stat. When alpha is equal to 0.5, we just look at the case that the agent will transition to the worst half portion successor stats, which means that we only look at the case that the agent will only transition to S1 in order to place more focus on bad situations. When alpha is equal to 1, our iterative CIVA RL model will reduce to the classic RL model. In this model, we define the value functions V and Q as the cumulative reward that can be attained when the agent transitions to the worst alpha portion successor stats at each step. And we define the optimal policy as the policy which maximizes the worst alpha tail of the reward to go at each step. So in our risk-sensitive RL model, iterative CIVA RL, the goal of the agent is to maximize the worst alpha tail of the reward to go at each step. In this work, we consider two popular performance metrics. The first performance metric is regret minimization. We define the regret as the cumulative gap of values between the optimal policy and the policies we actually choose. The second performance metric is best policy identification. In this setting, we are given a confidence parameter delta and an accuracy parameter epsilon. We need to identify an epsilon optimal policy, which satisfies that with probability at least 1 minus delta. The value of pi hat is no smaller than the optimal value minus epsilon. In this setting, we want to minimize the sample complexity. We define the sample complexity as the number of trajectories we used to identify the best policy.
Excuse me?
Yeah.
May I have a question in the previous page?
Yeah, sure. This page?
The previous one. Yes, this one.
Yeah, sure.
So I would like to know more about the intuition. So when you talk about the worst alpha portion in the value function, does it mean that if we cannot avoid a policy going to a bad situation, then we hope at least in the bad situation, we can still guarantee some sort of reward? Is that
the
right. Idea of? I see.
Yeah. We switch our objective from the average performance to the performance under bad situations, and we want to obtain good performance under bad situations.
I see. So is this like some sort of worst case analysis?
Yeah.
I see. So the idea is I want to guarantee even I'm in a bad situation, I can still perform not bad.
Yeah.
Right. I see. Thank you so much.
Thank you for your question. Yeah, let me continue. And first, we look at the regret minimization setting. In this setting, we design a sample-efficient algorithm. In our algorithm, in each episode K, we first use the CBAR-adapted optimistic value iteration to compute the optimistic Q-value function and the value function. And we set our policy pi k as the greedy policy with respect to the optimistic Q-value function. And then we play this episode K with policy pi k and update our estimation of transition probability. In this algorithm, we conduct the CBAR-adapted optimistic value iteration, and we employ the CBAR-adapted exploration bonus, which depends on 1 over alpha to efficiently explore the environment. And we assign more attention to the worst alpha portion successor stats in order to fit the goal of our iterative CBAR-RL model. For this algorithm, we provide a rigorous regret analysis. From Theorem 1, we can see that the regret of our algorithm is bounded by square root of K. Here, K is the number of episodes we play. Compared to classic RL, here in iterative CBAR-RL, the agent will suffer an additional factor of minimum visitation probability, min W. Here, min W denotes the minimum probability of visiting a reachable stat. The intuition behind is that since in iterative CBAR-RL, we place more focus on the worst alpha portion successor stats, the agent is more sensitive and more careful about bad situations. She must pay a regret due to exploring risky but hard to reach stats. So this is the reason why we will obtain an additional factor about the minimum visitation probability in our regret bound. In order to validate the optimality of our algorithm, we also provide a regret lower bound to demonstrate the tightness of this minimum visitation probability and the optimality with respect to K. In our lower bound, we prove that for some hard instance, for some hard MDP, any algorithm must suffer a regret depending on the minimum visitation probability. In the second performance metric, best policy identification, we design a sample efficient algorithm also based on optimistic value iteration. In this algorithm, we compute the estimation error based on the empirical conditional transition probability. This is the transition probability condition on that the agent transitions to the worst alpha portion successor states. So we want to compute the estimation error of value functions based on the conditional transition probability. Once our estimated error shrink within epsilon, we have a high confidence that we can guarantee the optimality of our hypothesized policy. Then we just output the greedy policy with respect to the optimistic Q-value function. This is our hypothesized optimal policy. For this algorithm, we also provide a sample complexity guarantee. From Theorem 2, we can see that the sample complexity of this algorithm also depends on this minimum visitation probability and a factor of 1 over alpha up to h-1. So our sample complexity depends on minimum between these two factors. Where alpha is small, our sample complexity will depend on the minimum visitation probability. In contrast, when alpha is large, our sample complexity will depend on 1 over alpha up to h-1. Note that when alpha is equal to 1, our problem reduces to classic RL with best policy identification. Then our sample complexity will match the result for classic RL. In order to validate the optimality of our sample complexity, we also provide a sample complexity lower bound to demonstrate the tightness of this minimum visitation probability. Furthermore, we conduct empirical evaluation for our algorithm. In our experiments, we tune the parameters alpha, delta, HSA to see if the change of the regret matches our theoretical bounds. So we validate our theoretical bounds and the effectiveness of our algorithm. From the figures, we can see that our algorithm, the radar curve, achieves a significantly lower regret than other RL algorithms. Furthermore, we also study an interesting limiting case of the iterative CIVA RL model. So this is what the question said. This is the worst case, a true worst case analysis. In this limiting case, we just focus on the worst tail, the worst case. In many safety critical applications, the worst case can be disastrous, like treatment failures. In this case, the agent is extremely risk averse and the risk level parameter alpha can approach to 0. In this case, var x will tend to the minimum x. The agent only focuses on the worst case. This is a non-trivial limiting case and cannot be solved by simply taking alpha approaching to 0 in our previous results. Because Both the upper bounds and the lower bounds for iterative Siva RL in our previous results depend on 1 over alpha. So we need to design new algorithms and develop new analysis for this limiting case based on the minimum operator. Next, I will introduce the problem formulation of this limiting case, worst path RL. In worst path RL, the Siva operator will become the minimum operator because alpha approaches to 0. And the value functions V and Q will become the minimum possible cumulative reward that can be attained. And the optimal policy will become the policy which maximizes the minimum possible cumulative reward. So in this limiting case, our goal becomes to maximize the minimum possible cumulative reward. In other words, we want to optimize the worst path. For this interesting limiting case, we design a simple and efficient algorithm. In our algorithm, in each episode K, we use the minimum operator-based value iteration to compute the empirical Q-value function and the value function. And we set our policy pi k as the greedy policy with respect to the empirical Q-value function. And then we play this episode K with policy pi k, and we update our estimation of transition model. From this theorem, from this algorithm, we can see that our value iteration here mainly based on the minimum value of our observed successor states. As the RL game proceeds, we will collect more and more observations of successor states, and our empirical Q-value function will become more and more accurate. The intuition behind this algorithm is that here the empirical Q-value function can only be overestimated. It cannot be underestimated because we mainly use the minimum operator. If the overestimation happens, our algorithm will be exploring an overestimated action and urging the overestimated Q-value to get back to its true Q-value. Otherwise, if the Q-value function is accurate, our algorithm just selects the optimal action. So our algorithm skillfully combines the exploration of overestimated action, which lead to undetected successor states and the exploitation of current best actions. For this algorithm, we provide a constant regret bound. From Theorem 3, we can see that the regret of this algorithm is a constant independent of K. K is the number of episodes we play. In this theorem, the first factor mean V pi SA denotes the minimum probability of visiting SA at least once in an episode over all possible policies. And the mean P as prime SA denotes the minimum transition probability over all successor states of SA. Here we can see that our algorithm enjoys a constant regret with respect to K. The reason behind is that worst path RL only cares about what next steps we can obtain, what next step we can achieve instead of specific values of transition probabilities. And this algorithm, under this limiting case, we only need to learn the connectivity among states, which only requires a constant regret. Here are some references. Thank you. Any questions are welcome.
Excuse me?
Yeah.
May I have a question on page 20?
Yeah, sure.
Yes. Thank you for your nice talk today. I'm wondering, when you replace this CVAR alpha, when you replace the original QPy term by this CVAR alpha, does it cause any analysis difficulties to reprove the Bellman equation and the Bellman optimality equation in this CVAR alpha version?
Yeah, good question. So when we change the classic expectation operator to the CVAR operator, so in fact, this is some kind of old topic called risk-sensitive MDP in the literature of operation research. So if you look at the operation research papers 20 years ago, there are some works introduce such models and prove the existence of optimal Markovian policy. So under such model, because we just replace the expectation operator to the CVAR operator at each step, so we will not break its Markovian optimal policy property. So we can still prove that there exists a Markovian optimal policy, and we can still establish Bellman equation and use the value iteration.
Okay, thank you. So if I want to learn more details about this technique, what are the keywords can I search? Can I get them from your paper?
Yeah. I cite the papers in operation research about risk-sensitive, or you can search keywords risk-sensitive MDP with and recurrent risk measures, or called iterative risk measures. Yeah, I can also share the link of the papers by email later.
That would be wonderful if you can share some link in the chat.
Yeah.
Thank you so much.
Just a minute. Hello, I typed the title and order of the reference in the chat window.
I see that. Thank you so much.
Yeah, you can also have a look at the relative work part of my paper. So I think I give a literature review. Just the section 2, the CVAR based MDP part. Yeah, in the operation research literature, while they discuss and they propose the model like MDP with iterative risk measures, their work mainly focus on studying the mathematical properties of such MDPs. So they are not RL works. They consider known transition model. And here we consider unknown transition model.
I see. Thank you so much. I think this is very nice that you introduced the advance in operation research to our community.
Yeah, thank you.
And because I joined your talk late, I have one more intuitive question in page 12.
Oh, yeah.
Yes, this one. So in the third remark.
Yeah.
So the reason why positive correlation induce a higher regret, is it because that when two arms are strongly correlated, then it is hard to distinguish which one is the best?
So the intuition is very straightforward because our decision space is continuous. So if you regard a weight vector W as an arm, so the variance of W is like W transpose times sigma star times W. So the variance of W is based on the covariance matrix. And so if covariance sigma star is positively correlate, the variance of W is larger. Then when you construct a confidence region, the confidence region often depends on the variance of arms. So because the variance is large, so the regret bound is large.
So yeah. I probably should correct my stating that it is because it is hard to shrink the confidence region.
Yeah. Because the factor of the confidence region is large. Mm-hmm. The estimation concentrates slower.
Slow. I see. Thank you so much.
Thank you. Thank you for your question.
Hello.
Hello.
If there are more questions in the chat box, can you also read them? Or maybe you can also open your mic to ask if this is more convenient for you. I saw there's a question around maybe 20 minutes earlier. Is that this regret guarantee to extend to showing epsilon convergence to the optimal policy in the chat box?
Yeah. I guess this question is asking if in the best policy identification part, if the epsilon dependent result reflects the convergence to optimal policy.
Okay.
Yeah. So
okay.
Yeah. So yeah, my understanding is that my answer is that given in this setting, best policy identification, basically it's a packed learning setting. Like it's not an exact computing. It's not exact learning. It's a packed learning setting. So given a confidence parameter delta and given a accuracy parameter epsilon, our goal is to output epsilon optimal policy. And if the accuracy parameter epsilon is more and more is smaller and smaller, the sample complexity we need to identify the optimal policy will be larger and larger. But we can guarantee that the output policy, the value of output policy is closer to the optimal policy. So I think when epsilon approaches to 0, the performance of our output policy is close to the optimal policy. But meanwhile, the sample complexity we need is also larger and larger.
Hope you can answer the questions. Perhaps if you have further questions, you can also email Yihan to ask.
Yeah.
All right. Since there are no further questions coming, then this is the end of today's seminar. Let's welcome again for Yihan's great talk today. Thank you very much.
Thank you, Jingfeng, and thank everyone coming here.
Yep. Okay. Then
bye-bye.